thank you, and thank you for giving me the opportunity to discuss a point which is generally not addressed in the energy scenario, and this is the need of mineral resources, mainly metals, for a low-carbon society. So my point here is that in order to produce clean energy, but also to store the energy and to distribute this energy, we will have to build an infrastructure which needs vast amounts of metals. And to produce these metals, we need energy and fossil energy. So we are entering a kind of vicious cycle, and we are trying to replace one fossil resource, oil and gas, by another, metals. So I am a geologist, and I am a bit far away from my field of expertise here. But I think that our contribution as a geologist is to first participate to the debate, of course, and trying to avoid developing technologies which are completely decoupled from the reality of mineral supply and mineral resources supply. So to go straight to the point, I'm showing here the evolution in the share of electricity generated using solar and wind and hydro sources. This figure was built according to the energy scenarios proposed by the International Energy Agency and also by Ecofis. This scenario has been presented yesterday. So what we see basically in this figure is that there is a very strong rise in the share of solar and wind electricity. So the problem of this, as you know, of these natural sources of energy, beside their intermittency, is that they are very diluted. And we need very large infrastructure to use this energy. An example is shown here. This is one of the latest generations of wind turbines produced by Alstom. So this guy is 200 meters high. The rotor itself is 150 meters in diameter. It has a 6 megawatt capacity. The basement goes down to 60 meters depth. It's made of concrete and steel. There is no gearbox here, but a permanent magnet, which contains, it's difficult to know exactly, but certainly more than 1 ton of rare earth elements, mainly neodymium, but also dysprosium, which is a very rare earth. The tower here is made up of more than 1,500 tons of steel. So the steel intensity of this wind turbine is about 250 tons per megawatt capacity, which is actually more than the steel intensity of previous wind turbines we can find in the literature. So it seems that with time we increase the steel intensity of these machines. But more important, it's almost 1 order of magnitude more than the steel intensity of nuclear power plant or dams. And we need about 900 of these wind turbines to produce the same energy as 1,300 megawatt nuclear power plant. So it's about 1.4 million tons of steel that we need here to produce the same energy. So the steel intensity of this wind turbine is also...
Sorry, on the previous graph, it was the steel intensity per installed megawatt.
Yes, your megawatt capacity.
Okay.
Yeah.
Installed.
Installed,
So
yeah.
effective is
installed.
Installed.
times higher.
So if we now look at the and the wind intensity is also higher than that of coal and gas-fired plant. So if we now try to define an average steel intensity for photovoltaics, it's much more difficult. So I'm just showing the range of values I found in the literature. So from 100 to 1,100 tons per megawatt. So we can make a rough estimate we need about 8,000 square meters for 1 megawatt electricity. Assuming that we need about 25 kilograms of steel per square meters, which is reasonable, it might be more or less depending on the installation, but in average it's something like that. It comes up that the steel intensity of photovoltaic is about 200 tons per megawatt capacity. And finally, for the concentrated solar power, the steel intensity is much higher, about 700 tons per megawatt, because we need really an infrastructure supporting the panels and also a motor to follow the sun and etc. So, well, we can report all these values on the same graph, and of course you see that the intensity, the steel intensity here for wind and solar technology is higher than for the technologies using fossil fuel. So we did the same calculation for other base metals like copper, aluminum, but also construction material, concrete, and glass. Glass is important here because it's what is called a crystal glass, which is used for the solar panel. It has to be very transparent, so the amount of iron in this glass must be less than 100 ppm, and it is made of using a very particular sand, which is not very common on the Earth. So this is also an issue. So now, using all this amount of material, we can estimate the material requirements for building the wind and solar facilities according to the scenarios I showed at the beginning of my talk. So I'm showing the results here for concrete, steel, aluminum, copper, and glass. The dashed lines here are the 2010 world production. And this is a cumulative amount, of course. So what we see basically here is that in 2050, the cumulative amount of concrete, steel, aluminum, copper, and so on, sequestrated in wind and solar facilities will be 2 to 8 times the 2010 world production. So these estimates are quite optimistic, actually. If we use...
How much is the current copper and aluminum and so on used for whatever current installations?
How much?
Copper is used for many other things.
Yes, sure. I'm only considering right now the wind and solar installations, not the other applications.
No, but I understand that the question is on comparing the yearly installations and the yearly production. Is that correct?
So, I mean, how much of the you can say
the fraction of the
production
world
in 2010 was used to make wind, solar, whatever energy facilities?
You will see. I will come to the point.
Well, this is for the world, is that right?
Yeah, yes. This is the global production. Okay? So now if we use the highest material requirement to build the solar and wind facilities, we can have very or more frightening results of this kind for all the elements we considered here. So the question is, should we worry? Well, actually, if we distribute now this amount of material we will have to produce until 2050 over the next 40 years, which is your question, we come to the conclusion that the base metal production will have to be boosted to 0.15 to 2% each of the next 40 years. What does it mean? Is it a lot or not? Well, actually, the present growth rate in the production of base metals is 5% since the beginning of the century. 5%, in the case of aluminum here, it's even a bit more. 5%, it means that we have to double the production every 15 years. And this is really frightening because we did that in the past, but now we have such a high level of production that doubling the production every 15 years is probably hardly sustainable over the next 40 years. So, and for this reason, we can imagine that the growth rate here will not, or that this trend will not continue. It is expected that production will stabilize in the future. We don't know when exactly, but this is something we already observed in the past. If we look at what happened after the Second World War, we see that we had between 1950 and 1975 an evolution and a growth rate of 7%. And then between 1975 and 2000, the production of aluminum stabilized at about 1 to 2%. Okay, so we can compare now the slope of this evolution of production between 1975 and 2000 with the evolution which is predicted only for building the solar and wind installations. And actually it's the same slope, which means that until 2050, do you have water somewhere? Thank you. Which means that until 2050, the increase in aluminum production needed to the construction of solar and wind facilities will be similar to that driven by all industrial sectors between 1970 and 2000. Well, we can do the same calculation for copper and iron, and the results are similar. So it's not only aluminum, but it's also copper and iron, which will have to be produced in mass. So now for glass and concrete, the production of these mineral commodities will have to be boosted to 208% respectively of the 2010 production, and more frightening, the case of rare elements that you probably already heard about that. We used a lot of rare earth elements, but not only rare earth, also rare metals in the, thank you very much. In the clean energy sector. And a study published 2 years ago showed that until 2030, the global demand in gallium, indium, selenium, dysprosium, neodymium, praseodymium, and terbium will have to be boosted to 10 to 230% of the 2010 world production. Question?
Yeah. How come that the range is so large, between 10 and 230?
Because it depends on the commodity you are looking on. Mm-hmm. It's based on the element. You have 10% here and 230% here. Okay? Yeah, it depends on the commodity.
Is it according to which deployment scenario for solar and wind facility? Because the future of these sources is quite uncertain for the moment, and you extrapolate to 2050.
Yeah.
So you need a scenario.
Sure, sure.
What is your hypothesis?
It's Is it clear? Okay, thank you. So the question is, again, can we make it? Well, there are two opposite views of the problem. The optimist will say that it's not a big deal. In any 30-year period in the past, mankind has consumed as much metal as during all previous history. And improvements of technology and the discovery of new deep-seated onshore and offshore resources will allow the trend to continue. So this is typically the business as usual approach, which is shared by people working for the European Commission here. This is a study on the critical metals in the path towards the decarbonization of the European Union energy sector, which has been published a few days ago. So I'm just showing one of the last sentences of this document. It's important not to overstate the risks of raw materials bottlenecks for key decarbonization technologies. This is because there are still many years before the large uptake of some technologies, and there are numerous options available to mitigate the risks identified. Well, for me, these options are not very clear, and this statement, if it is very optimistic, is not very clear, and for a scientist, it's not sufficient. The pessimist view is that doubling the production every 20, 30 years has been possible in the past. This is an observation. But as mines become more remote and metal grades decline, and above all, increasing energy demands will put a limit to the further expansion and the transition to a carbon-free society. To illustrate that, I'm showing here the results of a previous study that has been published quite a long time ago, actually in 2007, but the results are very interesting. The author tried to report the evolution of ore concentration, ore grades, for various commodities, copper, gold, and diamonds, nickel, and so on, with time. So starting from 1870 here. And what we clearly see is a general...
In the world or in Australia?
In Australia, sorry, only in Australia. What we see is a general decrease in the concentration of ores, these are, there are many implications for that. The amount of energy used to extract the same amount of metal, for instance, increases, of course, with decreasing the ore grades. This is what you see on this figure for uranium oxide. The concentration is decreasing from the right to the left here. And this is the amount of energy consumed per ton of extracted uranium oxide. The same observation for gold, but now the concentration is decreasing from the left to the right-hand side. And you see also this huge increase in energy consumption. The amount of material, the amount of rock which has to be displaced is also increasing with decreasing the ore concentration. And this is also a kind of pollution. The amount of carbon dioxide which is produced during the extraction also increases because we use fossil fuel here. Another point which we have to keep in mind, the localization of the reserve of all these mineral commodities. Well, most of them, which are reported here, antimony, barite, and so on, most of the reserves of these commodities are in poor countries where the gross national income per day and capita is lower than $2.5 a day in red or $10 a day in orange. So clearly these countries have generally structural difficulties, and they are not able, or they have limited possibilities to impose good practices of extraction, so and good social and environmental conditions of extraction. So this means that the technologies we have in developed countries in the mining sector and which try to minimize the impact, the environmental impact of extraction, are not used in such countries. So again, can we make it? So we have two views here. The realist, maybe you should say that we must ensure that the availability of raw materials, which is a fossil resource, does not become an obstacle to the energy transition. And for that, we have to understand the different issues. So my opinion is that there are two very different issues. The first one concerns base metals, glass and construction minerals, and the second one, what we call the high-tech or rare or critical mineral commodities. So in the first case, for base metals, I already said that the production of these metals increases by 5% every year. And the reason for that is the development of China. Not only China, not talking about Brazil and India and so on. China is nowadays consuming half the global steel that is produced worldwide. It's consuming half the copper and 1/3 of the copper and 1/3 of aluminum. And China does not produce all this metal domestically. It imports also a lot of metals. So this is a photograph of the ship bringing iron ore in one harbor of China. The participation of China in mining activities outside China is shown here. That was the situation in 2004 and the situation in 2010. The problem of this massive use of metals is that the prices, of course, are increasing. This is what I'm showing here. Between 2000 and 2008, the prices were, you can see, multiplied by a factor of 4 or 5 or even more. But it's not only the increase of prices, it's also the increase of the price volatility, which is an issue. This is the evolution of the copper price per metric ton, starting here in July or in October 2003, $2,000. 2 years later, $8,000. 2 years later, again, about $2,000, and so on. So this is really a problem because I don't know how economists are able to integrate these variations in their model on the long term. But also it's a problem for the mining industry because with such a volatility, they are quite reluctant to open new mines. And we can understand them because a mining project is about 20 years in time, starting from the exploration, to the first return. Okay, another consequence of this massive production of raw materials and metals is the amount of consumed fossil energy and greenhouse gases emission. Just to remind you, in 2011, 24% of the global energy consumed by the industry was used for the sole production of steel and concrete. So it's not negligible. Okay, so that was the first. That was the first problem on the base metals. But in addition to base metals, we have also the high-tech sector that uses a large variety of scarce metals in increasing quantities. So these high-tech sectors, it's of course the information, telecommunication sector, the transport, but also the clean energy sector. So the permanent magnet, as I said previously, of a wind turbine contains bore, neodymium, dysprosium. New technologies of solar panels here for photovoltaics in using a multi-layer technology involve gallium, indium, selenium. Gallium is not only used, of course, in this solar panel, but in LEDs, in every electronic device. At the beginning of the 80s or during the 80s, we needed 12 elements to make a computer. Nowadays, it's 45 elements or even more. So there is in a car, if you buy a car now, I'm not talking about an hybrid or electric car. A classical car contains 30 kilograms of rare earth elements. Okay, so it's a very competitive sector here, involving very different industries. Let's take an example, neodymium. Neodymium is an essential part of energy technologies, and by 2030, 300 gigawatts of additional wind power should be installed. With the technologies which are developed right now with the permanent magnet, it means that we should produce 10 kilotons of neodymium every year. 100 million of hybrid vehicles, 5 kilotons per year. The annual production of neodymium is 20 kilotons, and it comes only from China right now. The wind power in China in 2008 was 12 gigawatts. In 2011, it was 63 gigawatts. So China is almost doubling its wind capacity every year. And there is no reason why this should change, because the capacity of China for wind energy is really very high, and it is underused right now. So the China is using about 8 kilotons of neodymium a year, and you see the problem between these two numbers. So what is the solution? The solution is probably to open new mines, but at the condition that we find the good ores. Just talking about rare earth elements, I'm showing here the distribution of the different rare earth in the lateritic or in southern China, which is the main producer of rare earth right now. You see that we have a lot of yttrium, lanthanum, neodymium, and a significant amount of dysprosium, erbium, and so on. So the Americans decided to reopen their mine, rare earth element mine in Mountain Pass, which has been the main producer of rare earth elements during the 80s. If you look at the distribution of this rare earth in Mountain Pass, it's completely different. So you have almost no dysprosium, you have almost no yttrium. So clearly the reopening this mine in Mountain Pass will not solve the problem. An additional problem. Rare metals used so in the high-tech sector, including the clean energy, are not recycled yet. I'm showing here the recycling rate of different elements of the periodic table. What you see is that the base metals are recycled with a rate higher than 50%, but the commodities which are used in the green or the clean energy sector are in red, meaning that their recycling rate is lower than 1%. There are many reasons why they are not recycled. One of the reasons is that they are used in very diluted amount. So it's very difficult then to separate the different pieces, parts of a computer, for instance, which contain this rare earth elements, and then they are such diluted that there are thermodynamic limit to the separations. But we can improve that. Also, I'm showing here the increase in the complexity of metal assemblages in generic product. So there is no need for any comment here. So our knowledge of the resources and reserves of mineral commodities used in the high-tech sector is limited, and their recycling is very low. Moreover, the environmental cost associated with their production is very poorly known, because these elements are generally produced in countries where we have limited access, and it's very difficult to estimate the energy needs and the environmental impact associated with their production. And in any case, this energy and environmental impact is never included in the life cycle analysis, for instance, of wind turbines or solar panel right now. So at this stage, what I would say is that the classical view that base metals, glass and concrete are produced in large volume, and then they will have to be produced in even larger volumes, but our reserves and resources are large as well. Moreover, they present a high recycling potential. In contrast, high-tech metals have a limited potential of recycling. We have a poor knowledge of the resource and reserves, and their production is limited to few countries. So for these reasons, people started to think about the risk of supply of these raw materials over the last 5 years, and they define the concept of criticality, which is a risk assessment in the supply of this raw material. So the way they do that is plotting on such a diagram with an horizontal axis corresponding to the supply risk, and the vertical axis the importance to a particular industrial sector. say, the clean energy here. And of course, the elements with the highest score are the most critical. So the European Commission published a list of 14 elements which were considered the most as the most critical elements in 2010. Actually, it's more than 14 because we have the platinum group metals here and the rare earths. And then 1 week ago, a new list appeared with these additional mineral commodities. Okay, so of course, none of these elements are produced in Europe because the domestic production of Europe is limited to about 3% of the world production. Okay, so we are, I'm saying we, so in Europe, we are completely dependent on the importation of most of these elements. So this is the level of dependency to the importation. And in red, you have the elements which are produced in China, so for which China is the main producer. So for all these reasons, people generally think or say that these elements, these high-tech or rare metals are critical, whereas those ones are not. Well, this is a short to middle term vision and principally valid for the industry, and we understand why. But if we try to have a longer term vision, yes, the reserves are large, but the concentrated and easily accessible ores are declining. High recycling potential, yes, but the lifetime of a wind turbine is, let's say, 30 years. It means that during these 30 years, the metals will be sequestrated. You won't have access to this metal to recycle it. It will be possible just only after 2050. Another point is that the base metals have no potential for substitution. You will not be able to build a 200 meters high wind turbine using wood or bamboo or whatever. So steel is really, and concrete is really necessary, which is not the case of high-tech metals. High-tech metals are completely technology dependent. They are used since 20 years, and you are able to build a wind turbine without a permanent magnet. Okay, it will be less efficient. It will be, you will have problems, but it's possible. And for this reason, I'm not sure that these base metals and so on are really not critical or less critical. Moreover, it's not only a matter of feasibility. It's not because you can get a resource that you should use it. It's also a question of energy intensity and environmental and societal impacts of production. So to conclude, or almost conclude, I would say that the transition toward a low-carbon society requires the availability of a variety of metals and other mineral resources, and also fossil energy to produce these raw materials, because there is no track working with electricity right now. So we are trying to replace one fossil resource, hydrocarbons, by another, metals, and we will increase our consumption of energy and greenhouse gases emission. This is perfectly acceptable. I mean, I'm not trying to say we should avoid developing wind turbines and solar electricity production. This is completely acceptable, but at the condition that there is a decrease of CO2 production, for instance, after a reasonable period of time. And I think it's very important also if metals are recycled, because we are replacing one fossil resource by another. Okay, but metals can be recycled infinitely. It's not the case of hydrocarbons. Unfortunately, it's not the case right now. So we have to improve the recycling technology, the rate, but also the consumption of energy associated with this recycling. A comprehensive and precise estimate of these points is really necessary, and it remains to be done, actually. The difficulties is the access to the data. So it's very difficult to find a comprehensive list of material contained in a wind turbine or on solar panels or whatever. And not only for the turbine itself, but also for the rest. So all the infrastructure like grids and for the storage of electricity and so on. When you find the data, they are generally completely they are not interconsistent, and you have huge uncertainties. So that was an example for the photovoltaics here. Another example, which has been published by Sullivan et al. In 2010. This is the ratio of the energy used to produce, for instance, solar panels to the energy that it will produce during its lifetime. Okay? If you look at these values here, they range from 3% to 50%. 50%, it means that the solar panel will work during half its lifetime to produce the energy that was used to produce itself. So it's completely stupid. And it's not realistic. I mean, there is a problem in the data which have been published. But anyway, there is a large uncertainty remaining on this ratio. The same for the production of greenhouse gases associated to the production of these facilities. Here, you range from 7 to 140 gram equivalent CO2 per watt-hour. Uncertainty in the energy intensity also to produce the raw materials. This is the results of a study published by Yeli Shetty, also in 2010, showing that the energy required to produce 1 kilogram of steel, this is an average value, so the specific energy consumption in the steel industry, and this is a world average. You see that it decreased with time, starting from 1950, and nowadays the steel industry is likely to use 20 megajoule per kilogram of steel. This is not exactly the case if you take over publications. Here they show that the steel intensity is about 30 megajoule if you include primary extraction and recycling, and it is about 50 megajoule if you just consider the primary extraction. Okay, so of course, if you use this value or this one to make the life cycle assessment of your wind turbine, you will get different results. Huh? So this is my conclusion. The shift to renewable energy will need huge amounts of minerals, metals, and fossil energy. The lifetime of the solar and wind facilities is about 30 years, during which recycling won't be possible. And primary resources will have to be extracted to build the infrastructure of clean energy. I think it's really necessary now to have a precise and comprehensive evaluation of the energy and raw materials requirement in the energy scenarios which are available. A clear definition of the criteria to be minimized then is also necessary. Do we want to reduce the CO2 emissions, the cost of electricity, the type of energy generation, our national dependency to the importation of hydrocarbons, for instance, or do we want to play with many of these parameters? So clearly, I think the strategy will be different then. And in the meantime, I think it's really important to avoid developing unsustainable technologies, of course, gadgets, but that's another problem. But unsustainable technologies, I mean, in the sectors of the clean energy, and completely decoupled from the reality of raw material supply. It's probably necessary to optimize the ratio of efficiency to material requirements. So it's not necessary to absolutely want to increase the efficiency if the cost in terms of material content is not reasonable. Quantify the impact of novel technologies prior to their large-scale industrial development. We are talking about huge infrastructures here, so it's really necessary to quantify this impact before their implantation, and find new resources and improve the efficiency of metal extraction and refining. We have resources, we have reserves, so we will have resources for sure. Thank you.